Now that we've got all that about what a limit looks like, not a limit, a continuity, continuous function, stuff like that, we get into questions and things like this here. So we need to find what value for a makes this function continuous across all real numbers. Now, a couple few things. Notice the line, that's a linear equation. Linear equations are always continuous across everything. So less than 1, no problem. Radical functions are continuous everywhere in its domain. Well, the domain here is where x is greater than -8. Well, that's already less than 1, so all the values for x in the domain are a-okay. So three-part definition. So what is f of? The only issue might be, are these two connected? So what about at that change? What's f of 1? Well, that would use the second one because that's where the or equal to is. So 4 times square root of 1 plus 8, we get 12. So now the other piece, I probably would have checked that first, is, does the limit exist? Are they actually connected? Well, what is the limit as x approaches 1 from the left? And what is the limit as x approaches 1 from the right of f of x? Now again, why are we doing that? Because strange things happen. Left and right may not be going to the same number. Now, here's the thing. Since we want to make it continuous, we are going to force the equality. So plug in, so for the left, that would be our first piece up here. We're less than 1, so plug in 1. And so we get 6 plus a is that limit if we only knew what a was. Well, plug in 1 for x approaches 1 from the right, or when x is greater than 1. Direct substitution still. So we get 12. And again, we are forcing them to be equal because we want them to be continuous. We want this function to be continuous. So a is 6. That's it. Now, if you have more than one unknown, maybe a and b or whatever, you might have to get a separate equation. Sometimes setting the limits equal and using the function value to get a system of equations. All depends what it is, but this is the big piece, and most of them are going to look like this. Okay, now, what about continuity and stuff like that? Now, when we talk about continuous functions, the definition is at a single point. However, we can't look at every individual itty-bitty little point. So what do? We take a look at some things. Well, first of all, these functions are continuous on their domain. So no strange things going on. And what are they? Well, the first ones are nice, are the polynomials. And again, for polynomial functions, their domain is all real numbers. Rational functions, as long as we're in the domain, we're good. Like that one. What else was there? The radical functions, like square roots, cube roots, and stuff like that. Okay, even some trig functions. Like sine, cosine, even tangent, cosecant, because we eliminate the domain kind of thing. Piecewise, you can't plug in there because piecewise, the function may be, the value may be on the domain, but your right and left side may not connect. So we don't know that. Okay, so those are the main three. Oh, we got two others. Exponential, of course. Again, those are all real, domains are real anyways, and logarithmic. Now, what that does for us, is that when we're checking on questions like this, we can skip over that. But if we're checking for continuity, we have to go with each of them. So, right here, we have a linear equation, polynomial, and a cosine. So those are continuous across all real numbers, so c of x is continuous from negative infinity to positive infinity. B, okay, got this rational function. The only thing is, again, remember, on the domain, so what do we have? What do we have to exclude from the domain? That's right. Where's the denominator 0? In other words, where's f of x? Doesn't exist. So that would be x plus 2 equals 0, so x equals negative 2. So all of that, so this function f is continuous from negative infinity up to negative 2, jump over negative 2, and pick it up again to go positive infinity. Because again, that's where we had our vertical asymptote right there. You see how these things are starting to tie in together? Okay. How about C? Another rational function. Okay, what do we got here? Oh, wait. What about the domain? Well, can x squared plus 1 equal 0? Not really. If you imagine it, it can. Again, because that's a sum of two squares. Not real for the zeros. So, the domain is all reals, so is the function continuous on all reals. And lastly, piecewise function. So, up top, the first one here, where x is less than 1, cosine and 1, those two functions are good. So adding them up, those are continuous everywhere. So left of 2 is good. Polynomial function, x squared minus x, to the right of 2 is good. The only possibility is, do they actually connect at 2? In other words, we're actually checking, does this limit from the left side equal the limit from the right? And now you might say, wait a minute, I'm being a little bit, so left side, plug in 2, so cosine of 2 pi x, or 2 pi plus 1, 1 plus 1. Plug in, so from the right, where x is greater than 2, 2 squared minus 2. Woohoo! So the limit exists. What's the function value? Well, we actually, what's p of 2? Cosine of pi times 2, just 2 pi plus 1, we found earlier. So the limit is 2, because your right left side limits are equal. Function value is 2, so it's p of x is continuous at 2. So this piecewise function is continuous everywhere. Okay? That helps us with a lot of different things we can do, because if a function's not continuous, we can't do a lot of stuff across this continuity. Alrighty. So work on those and we'll go from there.